Okay, maybe I have to write. Okay. So you are in the right conference. Okay, it's not a dynamics conference. I just want to give some motivation for my work. A group G is said to have the Homomorph property if all matrix coefficients with no, any representation which is no invariant vectors are C0 maps, meaning this function G to pi G of et xi for any et xi vanish. And this is like a very dynamical property of the group. So don't worry because our examples are algebraic. Okay, so simple D groups have this property that all matrix coefficients vanish at infinity. And this actually, the Homomorph property was very useful in proving all sorts of theorems in algebraic groups. And it gives, for example, a very easy proof of this following theorem by Zimmer, that GB, a locally compact group with a Homomorph property, then any continuous map, homomorphism from G to H, to any locally compact group, H, the image of G will be. And some observation called it theorem by Zimmer. And he actually saw this as saying that simple D groups are really simple. Like algebraically, they're simple because, they map, take the group structure to the group structure, there's no kernel. And topologically, they're simple because they map, homeomorphically wherever they sit. So this is like how Zimmer saw them. And this motivates the following definition. And what we're going to talk about today mainly is some closed image property. So a group G is said to be sealed, like really closed, if under any continuous homomorphism into any Hausdorff topological group. Now, I don't assume H to be locally compact anymore. The image of G is closed. So this is our new property. And for example, yes, it's true that also simple groups over local fields have this property, in particular over QP and so semi-simple. And even in the paper of Bader and Gelander, they studied quasi-semi-simple groups, which you can have automorphism of trees and so on. But they have some paper where they generalize Homomorph property and they get free. And the question is, what other algebraic groups have this property? And the answer is the following. If I have some connected algebraic group over a field K, now I will assume the characteristic is 0, then the group G is sealed if and only if the centralizer of the Levy part is anisotropic. It's a fancy way to say that the centralizer of the Levy part is compact. And it's a fancy way of saying that the Levy part is basically semi-simple, and it acts with no fixed points on the unit. No, for the whole group. The whole group has the group is not reductive yet. Exactly. For the reductive group, we have so this is a generalization. And for example, we just take what we know and we add this, unipotent part, and it still works. These groups are still sealed. It's yes, product of two seals, and even an infinite product. So let's see what's not going on, right? Because we don't have R there. So we know that we have R and we have a non-closed image, right? We have this irrational winding around the torus with a non-closed image. And what's the problem here? Why is this not good, besides the fact that it's not sealed? I can pull back a topology from the image back to the domain. Okay, so I take an open set in the torus, has this infinitely many lines. I pull it back. I say, oh, this is an open set now on my domain. And I get a new topology on the domain, which is still a group topology. It's still Hausdorff, the map is injective. And it's a weaker topology because, notice that any open set here is unbounded. So it's definitely not the same topology. It must be weak. Okay, so this is what's going on and motivating a bit more subtle property called minimal. So we call a group G minimal if the topology it has is minimal. So we start with a group with a topology, and we say that it's minimal if there's no weaker group topology on. Okay, so for example, the real line is not minimal. We just saw, right, that we can pull back. Does not, yeah. See, that's right. And equivalently for G Polish, it's just really the same as saying that any injective map is closed. Okay, so this is a closed image property as well. And some examples, so compact groups, of course, every image is closed. Sealed groups, in particular compact groups, are sealed. not R. What about SL and Z? Does it embed non-closed somewhere? In many places, right? Pick a P or for finite completion, whatever you want. What about QP? Can you do this torus trick with QP? And then it will be not closed. So it's a question I'm asking you, yeah. Okay. Yeah, it's just a warm-up, yeah, okay. Yeah, okay, and these are not, yeah, not and not. So both not, and why not QP? I mean, first of all, there's a general fact, which minimal and abelian must be compact. QP is not compact, but an easy proof for locally compact abelian groups would be just look at their Bohr compactification. It embeds inside, so it can't be closed. So if, and another fact, if G is minimal, its center is minimal, in particular, it's compact, it's abelian. So if we're looking for examples, we need groups with compact center. Okay, and SL and Z is compact center, but it's not an example. So what does work? Here's a theorem by Gopal and Omori, theorem back in the 70s papers. So if G is a connected affine algebraic group over R, then GR is minimal if and only if the center is compact. It did not state in this language, but it's basically what they're saying. So for real groups, having a compact center is the same as being minimal. Okay, so real groups, this is if and only if. Fast forward many years later, and we get the same thing for algebraic groups over local fields with characteristic 0. Again, if the center is compact, my group is minimal. So this is exactly analogous to Omori and Gopal's result. And actually, we do not have case analysis, and we do not use their results in order to get this in general. We actually prove using structure theory. And we will now see a quick sketch of how this can be done. Okay, so for example, of course, a group which is not sealed but is minimal will be this QP star times QP. In the theory of minimal groups, there's this long history between the 70s and the 20s. There's a whole theory of minimal groups. No one talks about algebraic groups, but they talk mainly about R star, semi-direct R, and other generalizations of. But now we're back to algebra. So let's see how we prove the minimality. So we start with this group with a compact center. First, we find this solvable group with a compact center, and the solvable group is co-compact. Okay, and if there is a Borel, you take the Borel. If not, you take the solvable part of the minimal part, and this will work. So how does minimality of B will imply minimality of G? Suppose I have an injective map from G to H. I want to show that the image is closed. So B is minimal. So F of B is closed, meaning this will be Hausdorff. B is co-compact. So G mod B will be compact. This is compact. This is Hausdorff. Then this map, the image here is closed. And then I just, go around this way, and I get the image of. Okay, so minimality of B will just imply minimality of G. So really, in order to prove minimality, I just need to prove for solvable groups. Great, so let's prove for solvable groups. And solvable groups, again, have this wonderful semi-direct product where T is some torus and U is this unipotent group. And the proof for minimality will follow from these two claims. Claim one is the following. If I have some weaker topology, and when I say weaker, I mean weaker than the K-point topology. Okay, we're over K, so implicitly the topology, I mean, as if matrix is over K. So all weaker topologies coincide when restricted to U. That's claim one. And the second claim is that all weaker topologies coincide on the quotient B mod U. So the quotient topology is just pushing the open set. So if I have two different topologies, they may be different, but they may coincide in the quotient. They may be different if they may coincide on the subgroup. Anyway, if it happens both, then the topology will be the same. So in order to really proof sketch something you'll believe me for a solvable group, let's assume that U is a abelian and everything will be much easier. Okay, so let's assume even more that the action of T on U is irreducible. Okay, so we have like a really simple case, a torus acting irreducibly on some vector space. and we have the group T semi-direct product 2, and we need to show that it's minimal. So what do? We have T acting irreducibly on U. We use Schur's lemma, and we get that this map from T to the endomorphisms of U is actually interpreted as a scalar multiplication on U. In what sense? I didn't see. Okay. So why am I looking for scalar multiplication? Sorry. We know that U is not minimal, right? A vector space with additive topology is not minimal. It's not compact, and it's abelian. But we have another fact that we know that topological vector spaces of finite dimensions are unique, right? So it is minimal. And the reason is that we have another constraint, which is the action or the multiplication, the scalar multiplication is to be continuous. So if we just kind of find something like a scalar multiplication, which will act on U, we will have this minimality again. So how do we get this scalar multiplication? The torus acts on U, and we can cook up from this torus acting on U scalar multiplication, but it won't be the whole multiplicative group acting. It will be some analytic subgroup. And when I mean analytic subgroup, I mean that T is defined over K, and the endomorphisms of U, which is actually isomorphic. We can show it's isomorphic to a field, K prime, which is some finite extension, and T maps to K prime, into the multiplicative group of K prime, as an analytic subgroup. And we show that multiplication by some analytic subgroup is enough to ensure minimality. So you don't need to have scalar multiplication by the whole field, just by some small subgroup of the multiplicative group, and you're fine. So that's enough for uniqueness. For the other direction, so now we know that all topologies on U are the same. We want to show that topologies on B mod U will be the same. Notice that B acts on U. U is normal, right, the unipotent part. And U is abelian. So of course it factors, it's in the center of the action. So B mod U now acts on U. And here again, I really use the fact that U is abelian. Otherwise, B mod the center would act on U, and I had to do some other games. And then we get this embedding of B mod U into GLU. Okay? And recall that here, the weak topology is equal to the usual one. So this is really GLU, the regular GLU that we know. Then we have strong topology maps to the weak quotient topology, which maps into, again, the usual topology, which is strong. So we have this kind of sandwich, which will make both topologies. So we showed claim 1 and claim 2. Claim 1 meaning topologies coincide on U, and claim 2 meaning topologies coincide in the quotient. And there's a famous lemma called Merson's lemma, which says that if we have some subgroup, it doesn't even have to be closed either. Just some subgroup where both topologies coincide on it and on the quotient, then both topologies are the same. So this proves the theorem for B, and proving for B will prove for G. Great. So where did I use the characteristic assumption? Because I want to appeal to some people in the audience here, which are really experts on positive characteristic, and maybe they can help me finish this criteria. So we had this map from T to the endomorphisms of U using the Schur's lemma, but this map may not be separable. And recall that we needed the image to be analytic. It's usually not a problem. For all cases, I can always go to even a smaller local field. A K-analytic, yeah. So, yeah, exactly. So, yeah, and the second idea is that the unipotent radical might not even be case split. I mean, or even defined. So yeah, so we can. I'd be happy to have this talk with you later, because there's a few ideas here which I'm thinking how to exploit what can be known, and maybe actually get this. And Sury reductive groups, yeah. Yes, so I have tried to read this. I actually say that, and yeah, that's another reason I'm happy to be here, and this work relates to Gopal as well. And so using a tiny bit more of structure theory, we want for general groups, we get minimalities for all groups with compact center. We'll see the property. We can talk about it next time. Let's finish now with our weekly almost simplification. So we have a topological group, and every topological group has this universal compactification, which is a semigroup. And if I'm locally compact, they actually embed inside. And when I mean semigroup, I mean semi-topological semigroup. So it's S, such that the multiplication S times S to S is separately continuous. So usually in topological group, we have to be continuous on both arguments. To be semi-topological, we need to be only continuous separately on each argument. And there's a universal one, meaning any other compactification will factor through it. The timer is not working. So here's a theorem. It says 24. It's because I had a proof and I noticed a little bit of a bug, which I'm fixing now. So let's say 24. Let G be a connected finite algebraic group over a local field. Again, this is our setting, 0. Then we have this uniform universal compactification, the WAP compactification. Then for any S in infinity or any S at all, right? This is, of course, true for S and G. The set S times G equals G times. This is very useful when going to representation theory. This will give us the following our result, saying that matrix coefficients of these groups of GK, now I assume that they're minimal or that they have a compact center, you know, it's a fancy way to say compact center now. So minimal GK, any matrix coefficients of a faithful irreducible representation will vanish at infinity. And once again, we have another uniform proof of Homomorph, because take some simple group, take a representation, factor it to its sum of irreducible representations or integral of irreducible representations. And they're all faithful because the group is simple. And vanishing of matrix coefficients will just vanish for them all. So here we have another uniform proof, but it's a bit more subtle. So like we can get a few other results from this, which are not, you know, general Homomorph, all unitary representations. And it follows from these two quick observations. These are not observations. These are observations by Veach and a few other people, like in the 70s and 80s. So matrix coefficients of the unity representations will vanish. It's a weak operator topology. The closure is just the one-point compactification is 0, right? Because these matrix coefficients are exactly 10 to 0, just means that they tend to 0 in this topology. And the weak operator closure is a semi-topological semigroup, and then we can use the lemma we did before and play around with the theory of topological semigroups and get this theorem that we had. And that's what we have for today. So,
thank you for this talk. Are there any questions?
Hi, yeah. So, so in characteristic P, I guess, I mean, one thing is the solvable group, of course, may not split as a semi-direct product of a torus against a uniput, and that's one difficulty. But I slightly didn't understand, you were passing to the solvable case, right? How did you do that? I mean, while also saying G mod B was compact, but what if you didn't have a Borel over the base field? What was?
So you have a minimal parabolic. If you don't have any parabolic, you're compact.
Sure.
You have a minimal parabolic. And minimal parabolic have this, so if P is a minimal parabolic, it has this decomposition state.
Right.
Where this is a minimal parabolic of the unipotent product. And this is actually a centralizer of a torus.
Right.
This universal compactification, is it related to the kind of compactification which Venkatramana was thinking of? What happens, for instance, for SL2Z?
So SL2Z, I think it's a crazy compactification because this universal compactification is like topological. So I think for SL2Z or for discrete groups, it might actually be the Stone-Czech compactification. I'm not sure. Or okay, it's a Samuel compactification. It won't be a bit better, but it's still better.
There are no further questions. Let's thank the speaker again.